Hello, this lecture is about deflection of beams. It is chapter number 9 of the textbook of Mechanics of Materials by F.P. Beer and Johnston. The same lectures, the PDF slides of these lectures can be obtained from my Google site, which is sites.google.com/viv/atta85. If you click on student resources, you can find the lectures here, lecture of this subject and even the other subjects. Coming back to the lecture, in this chapter we will study about deflection of the beams. Before this, we have already studied some other topics related to beams. Previously in chapter number 5, we have discussed about strength, moment and shear force in the beam. Previously, we have studied about shear force and bending moment of the beam. For example, if we have a beam, previously by sectioning the beam at any point, we can find shear force and bending moment in the beam. Using this shear force and bending moment, we can find the shear stress and bending stress in beams. Now in this chapter, we will further study deflection and slope. What is deflection and slope? For example, if a beam is under force, transverse force, it will deform and there will be deflection in the direction of the force. This deflection y will be calculated in this chapter. How to calculate it, we will learn different methods. And similarly, the slope of the deformed curve theta at any point. So we will also study it in this chapter. So going further in this chapter, before going further, I will recall one of the expression which we have previously studied. 1 over rho is equal to m over ei. This is expression for the curvature of the beam, where 1 over rho is curvature and rho is called radius of curvature. We will use this expression to calculate, we will use this expression to further derive expressions for y and theta. So let us go and do it. This expression 1 over rho equal to moment divided by ei can be used where moment is a function of x. What is x? X is length of the beam. If a beam has a total length of L, x is 0 at one end and it is equal to length L at the other end, and it varies between 0 and L. So by putting different values of x in the function of moment, we can find different values of 1 over rho curvature of the beam. For example, at x equal to in this beam, moment is equal to px. So at x equal to 0 at the left end, if we are counting x from left to right, at the left end x is 0, so 1 over rho will be 0, and at the right end x is equal to L, so 1 over rho is not equal to 0, and rho can be found as ei over pl. Well, by using this expression, we can derive general expressions for y and theta. How we will do it? Before that, we need to discuss some other facts. Here's a case. This is a overhanging beam. To solve this beam and to know about the curvature 1 over rho, we first need to determine the reactions at point A and point C. After finding the reactions, we need to draw a bending moment diagram because the curvature depends upon bending moment, so we need bending moment at each and every point. Here we can see here are two concave curvatures, here and here at point B and C. So we can see bending peaks in the bending moment diagram at the curvature points. For example, here is an upward concave curvature at this point. So here is a positive moment. Here is a downward concave curvature. So we have negative moment. So where there is a maximum moment of 6 kilonewton meter, there will be maximum curvature at point C. From our previous studies of elementary calculus, we know that 1 over rho is equal to d square y by dx square divided by 1 plus dy by dx square all to the power 3 by 2. Here 1 over rho is curvature, y is deflection of the beam, we can see it here, it is deflection, and dy by dx, which is actually slope. The y deflection of the beam is usually a small number, so its derivative will be even a smaller number. So we can neglect square of a smaller number, which is dy by dx square. It is almost equal to 0. So we can simplify this expression as 1 over rho almost equal to d square y by dx square. Previously we know that 1 over rho is equal to moment divided by EI. 1 over rho equal to moment divided by EI. If we compare these two expressions, 1 over rho equal to d square y by dx square and 1 over rho equal to m over EI, we can write as m over EI is equal to d square y by dx square. Or we can say that EI d square y by dx square is equal to moment. Well, now it is a double differential of y. In order to get y from this expression, we need to integrate it twice. So by integrating it once, we can get EI dy by dx. This dy by dx can be written as theta as well. So we can write it again, EI theta is equal to integral of moment plus constant of integration C1. Well, so this expression gives us theta, which is slope. Integrating it once more, we can write it as EI y. Differential integral of dy by dx is y. It will be double integral of moment is also dx plus c1x plus c2. These two expressions are very useful to determine slope and deflection along the beam curve at any point. We can simply put value of x and we can get values of y and theta. Here are two unknowns, c1 and c2. First we need to find these two unknowns, c1 and c2. These can be found by knowing the boundary conditions of the beam. Here are two unknowns, so we need at least two boundary conditions to get two equations to solve and calculate these two unknowns. So what can be those two boundary conditions? The boundary conditions are always different for different types of beams. So in this course, specifically, we are studying three types of statically determinate beams. So for those, we will discuss their boundary conditions. These are the three statically determinate beams. The first one is simply supported beam. Simply supported beam. In this beam, we can see that there is no deflection at point A and no deflection at point B. A and B are supported by two supports. One is A supported by a pin support, B supported by a roller support. So there is no deflection at support points. So X for simply supported beam, when X is 0, Y is 0. Similarly, when X is equal to length L, Y is 0. At these 2 points A and point B, Y is 0. Another type of beam, which is overhanging beam. In this beam, again, we can see there is no deflection at support points A and B. So we can see, for example, there is a distance A between point A and point B. You can say at X equal to 0, Y is 0. At X equal to A, Y is 0. Well, here is another type of beam, cantilever beam. In cantilever beam, we have only one support, but it is a fixed support. At fixed support, there is no deflection. So at X equal to 0, Y is 0. But at fixed support, if we draw a tangent line to this curve, this tangent line has zero slope. So we can also say at X equal to 0, slope is 0, theta is 0. So these two boundary conditions can be used to find two unknowns C1 and C2. In case of simply supported beam, we have two boundary conditions, both related to y. Y equal to 0, y equal to 0. So both of these boundary conditions can be inserted into expression of y. Similarly, for overhanging beam, we have two boundary conditions, both related to y. These two can be inserted into expression of y. For cantilever beam, we have one expression for y, the other for theta. So this one can be inserted into expression of y, but this expression should be used with expression of theta on the previous slide, this expression. So by using boundary condition for any kind of beam, we can calculate the unknown constants C1 and C2. How we will do it? We will do it in our example problems on the next slide. Okay, here's an example problem. It is a concept application 9.1. Very important. The cantilever beam AB is of uniform cross section and it carries a load P at its free end A. Determine the equation of elastic curve and deflection and slope at end A. Determine the equation of elastic curve. What is the equation of elastic curve? It is very important. It will be asked in almost all of the questions to determine the equation of elastic curve. Equation of elastic curve is equation of y as a function of x. So we have to find this expression. Expression of y, deflection as a function of x length. So first part, we will derive this kind of expression. In the second part, we have to find deflection and slope at A. Deflection at A, YA, and slope at A, theta A. They are unknown. So once we get expression for y, general expression for y, we can put corresponding value of x. What is x at A? Here x is 0. When we put x equal to 0 in this expression, we will get ya. Similarly, we will derive another expression, theta is a function of x. when we put x equal to 0 in this expression, we can get theta a. So let us solve this problem. Solution of the problem of this problem is given in the textbook of the subject Mechanics of Material by Beer and Johnston. I will solve it here. Okay, what we have is a cantilever beam fixed at the right side, point B, and a load P is applied at point A. Total length of the beam is L. Okay, before solving this problem, let us discuss one important point, that moment between A and B has a single function, because there is no other load between A and B. There is only one load, P. So for all such kind of problems, we need to determine moment first. So why do we need to determine moment? Actually, we have this expression EI d square y by dx square equal to moment. If we find moment as a function of x and we put we integrate it twice, we can find y from this expression, theta and y. So first we need to determine the expression for moment. We have to section this beam between A and B. Total length of the section is x. Here will be shear force and a moment. X varies between 0 and L. Okay. Moment from this diagram we can calculate it using equation of equilibrium, summation of moments. Let us consider counterclockwise moments as positive, summation of moments equal to 0. So we can see that m plus px both are counterclockwise, their sum is 0. So m is equal to minus px. This m can be inserted in this expression and then we can integrate it twice to calculate y. So let us do it. Simply put m equal to minus px in the above expression. Now we can integrate this expression twice. How we can do it? By integrating it once, we can write EI theta equal to integral of minus px. It will be minus 1 over 2 px square plus there will be constant of integration c1. Let us call this expression as equation number 1. Now integrating it once again, EIY is equal to integral of x square is x cubed by 3, so it will be minus 1 over 6 px cubed plus integral of c1 is c1x. There will be another constant of integration c2. Similar to our previous discussion, we have got two equations, one for theta and the other for y. There are two unknowns, c1 and c2. These two unknowns can be determined if we have two equations. For that we need two boundary conditions. This is a cantilever beam. For cantilever beam we have 0 deflection and 0 slope at fixed end. Here the fixed end is on the right side. Here x is equal to L. We usually start from left side. On the left side x is 0. On the right side x equal to L. Y is 0 and theta is 0. We have previously discussed that in the cantilever beams, at the fixed end, y will be 0 and theta will be 0. So let us put x equal to L and theta equal to 0 in equation number 1. So put x equal to L and theta equal to 0 in equation 1. We will get C1. You can do it by yourself. I will directly write C1 equal to 1 over 2 PL square. The solution is available in the book. Okay, now to find C2, put x equal to L and y equal to 0. As this boundary condition is related to y, so we have to put in equation number 2 which belongs to y. So put x equal to L and y equal to 0 in equation number 2. C1 is already known, 1 over 2 PL square. So by simplifying equation number 2, we can get EIY equal to minus 1 over 6 px cube plus 1 over 2 p L square x. By putting x equal to L and y equal to 0 in equation number 2, first we have to find C2, which should be minus 1 over 3 PL cube. You can do these calculations by yourself by simplifying equation number 2. Okay. Now we will put C1 in C2 in equations 1 and 2. Put C1 and C2 in equations 1 and 2. We will get equation 1 will become as EI theta equal to minus 1 over 2 px square plus 1 over 2 PL square. This is expression for slope theta, and equation number 2 becomes EIY equal to minus 1 over 6 px cube plus 1 over 2 PL square x minus 1 over 3 PL cube. This expression can be further simplified by keeping y on the left side and all of the other terms on the right side. We can rearrange this equation as y equal to p over 6ei into minus x cube plus 3l square x minus 2l cube. This expression can be called equation of elastic curve because it is in the form of y as a function of x. This was required in the first part of the problem to determine equation of elastic curve, which is y as a function of x. Then we were asked to find y at point A and theta at point A. At point A, x is 0. So let us put x equal to 0. In equation number 3, we will get theta at A, and in equation number 4, we will get y at A. So put x equal to 0 in equations 3 and 4. you will get theta and y a. I will write it directly here. You can do the calculations by yourself. Theta a will become PL square divided by 2 EI, and YA will become minus PL cube divided by 3 EI. This negative sign shows downward deflection. We can see that this beam will deflect downward. Similarly, the positive theta shows counterclockwise rotation. So in the cantilever beam of this problem, we can see it is like this. It will deflect this form. YA, it is downward, so it is negative, and theta A is counterclockwise, so it is positive. We can remove this negative sign and put a downward sign here. With YA, it will be fine. Okay, so this was solution of concept application 9.1. What we have done, actually, we have started with this expression. We have to start all the problems with this expression. EI d square y by dx square is equal to moment. Then we have to find function of moment, which can be found by sectioning the beam between the 2 points, whichever points are mentioned in the statement of the problem. In this problem, there are only 2 points, A and B. So by finding the moment using equations of equilibrium, we can put the expression of moment in the first expression, in this expression. Then by integrating it twice, we can find general expressions for theta and y. Here will be two unknowns, C1 and C2. These two unknowns can be found using two boundary conditions. In this case, in cantilever beam, at fixed end, theta will be 0 and y will be 0. So we have found C1 and C2. Putting C1 and C2 in the general expressions for theta and y, we can get expressions for theta and y. All of the terms are known. This expression for y as a function of x is equation of elastic curve. By putting x equal to 0 for point A, we can find theta A and ya. Similarly, there are other concept applications in this book. Concept application number 9.2 and 9.3 on the same topic, but those are related to simply supported beams. One is for distributed load and other is for concentrated load. So I recommend you to solve to try concept applications 9.2 and 9.3 from the same textbook. Hopefully they will help you in understanding this topic more. Okay, moving forward, here is a sample problem 9.1 from the same book. The statement is, for portion AB of the overhanging beam, we have an overhanging beam. There are 3 points, loaded points A, B and C. There is a reaction at A, reaction at B, and an applied load P at C. This is overhanging beam. So moment function will be different between AB and between BC. Okay. So we are asked to consider portion AB only. So we will have a section between AB. For the portion AB of the overhanging beam, derive the equation of elastic curve. For part A, we are asked to derive an expression of y as a function of x, equation of elastic curve. Whenever it is asked to derive equation of elastic curve, we have to derive an expression of this form. In part B, determine the maximum deflection, y maximum. And in part C, we are asked to evaluate y maximum. What is the difference between part B and part C? In both of the parts, we are asked for maximum deflection, but part B is to determine maximum deflection, means a general expression for y maximum. And part C is to evaluate a numerical value of the y maximum. So once we get a general expression for y in part A, how we can find y maximum? For any function to be maximum, we have to consider its first derivative equal to 0. By considering first derivative of y equal to 0, we will find a corresponding value of x, and we can get y maximum, expression for y maximum. And then by putting all the numerical values given in the general expression, we can evaluate y maximum. So we have to follow the similar procedure as we have done in our previous problem, concept application 9.1. We have to start with this expression ei d square y by dx square equal to moment. This moment must be for section AB of the beam, because we are asked for portion AB only. Okay. In order to determine this moment, we need to know the unknown reactions at A and B. So first we have to use our knowledge of statics to determine reactions at A and B, which you can do if you know statics. So it is already done in this problem. RA and RB, two reactions. Reaction at A is equal to PA over L. It is downward. If you are considering it upward, then the value will be negative. Okay, RB is upward. It is equal to P into 1 plus A by L. I assume that you can calculate reactions using your knowledge of statics, using equations of equilibrium. Now, by sectioning the beam between point A and B, we have this section, and we can calculate moment, which will be minus PA divided by L. This x is between A and L, so it is between 0 and L. A and B, so it is between 0 and L. Okay. Now we have to put this expression of moment in this general expression ei dy by dx, d square y by dx are equal to moment. So by putting moment equal to moment as a function of x in this expression, it will become ei d square y by dx square equal to minus pa over l x. Now integrating this expression twice, we can get expressions for theta and y. So it is already done. This is expression for theta. D square y by dx square is theta actually. And eiy equal to something. C1 and C2 are two unknowns, constants of integration. In this diagram, we can see there are two supports at point A and point B. At support points, y must be 0. So x equal to 0, y is 0. At x equal to length, y is 0. So by putting x equal to 0 and y equal to 0 in this, let us call them expression 1 and expression 2. By putting x equal to 0 and y equal to 0 in expression number 2, because this is related to y, so we have to put in expression of y. C2 becomes 0. Again, by putting x equal to L and y equal to 0 in expression number 2, we get C1 equal to 1 over 6 PAL. Now substituting C1 and C2 in expressions 1 and 2, we get expression for dy by dx r theta and expression for y. This y is equation of elastic curve. This is y as a function of x. It was required in the first part of the problem. It is already done. Now in the second part, we are asked to determine expression for y maximum. For y to be maximum, its first derivative must be equal to 0. here is its first derivative. This must be equal to 0 to find the value of corresponding value of x. So let us put dy by dx equal to 0. In the next slide, dy by dx equal to 0. So we can find x. This is the value of x, 0.577 L, for which y must be maximum. By putting this value of x in the expression of y, we can get y maximum, which is 0.0642 PAL square divided by 6EI. This is general expression of y maximum, which was required in part B. It is solved. In part C, we have to evaluate y maximum. So for numerical value, we have to put corresponding numerical values of I, E, P, L and A. L and A both are in feet. We have to convert them into inches. 1 foot is equal to 12 inches. So by multiplying L with 12 and A with 12, and P is given in kilopounds, so it is 15 to 10 power 3 pounds. By inserting all the numerical values in this expression, our next topic is direct determination of the elastic curve from the load distribution. Until now, we have used moment function to derive expressions for deflection and slope. Now we will use distributed load function to derive the same expressions for slope and deflection. Here we have already studied that differential of moment is equal to shear force. So similarly, we can say that we have already discussed in our previous chapters that differential of shear force is minus load function. If we differentiate the moment function twice, this one, so the moment function, double differential of moment function will be equal to first derivative of the shear force, which is further equal to load function minus wx. W is a function of x. We already know that moment is equal to EI d square y by dx square. If we integrate this function, if we differentiate this function twice, so this function will be also differentiated twice, so it will become fourth order differential equation. So we can write this as d square d square m by dx square equal to EI d power 4 y by dx power 4, which is equal to minus function of load. Further, this is a fourth order differential equation. If we integrate it 4 times, we can derive an expression for deflection. If we derive it for the first time, it will be EI d cube y by dx cube. This itself is equal to shear function, and the right hand side can be integrated as integral of load plus C1. C1 is constant of integration. This function is also equal to shear force. If we integrate it once more, it will be EI d square y by dx square, which is equal to moment, and the right side will be double integral of load plus C1x plus C2. Integrating again, we can write it as EI dy by d theta, or we can dy by dx, or we can directly write theta, which is slope, and it will be triple integral of the load function c1x. So integral of c1x will be 1 over 2 c1x square. Integral of c2 will be c2x, and here will be another constant of integration c3. Integrating once again, here we have ei y is deflection. Here will be 4 integrals of the load function plus integral of x square will be x cubed by 3, so it becomes 1 over 6 c1x cube plus 1 over 2 c2x square plus c3x plus c4. This expression contains 4 unknown integration constants c1, c2, c3 and c4. These constants can be determined if we know at least 4 boundary conditions. Previously we had only 2 constants of integration c1 and c2, and we needed 2 boundary conditions in each case. Now we have 4 unknowns, so we need 4 boundary conditions. So here in this beam, which is a cantilever beam, we already know that at the fixed end, where x is equal to 0, at the fixed end where x equal to 0, we have deflection equal to 0 and theta equal to 0. We can put these boundary conditions into deflection equation and slope expression. Similarly, at x equal to L, we have shear force equal to 0 and moment equal to 0. So we can use these expressions, shear force equation and moment expression. So totally we have 4 boundary conditions, and we can find 4 unknowns c1, c2, c3 and c4. Similarly, in a simply supported beam, at x equal to 0, we have deflection equal to 0 and moment equal to 0. There is no moment at any point where there is no fixed support or no concentrated moment. So at pin support, shear force deflection is 0 and moment is 0. So we can use the first boundary condition, deflection boundary condition, in this expression, and moment boundary condition in this expression. Similarly, at x equal to L, again deflection is 0 and moment is 0. So we can put deflection boundary condition into the deflection expression and moment boundary condition into moment expression. At all the pin supports and roller supports, there is no moment, remember it, but there is a reaction force, so the shear force will not be equal to 0. Similarly, at free ends like this, where there is no concentrated force, so there will be no shear force, and even there will be no bending moment. At all fixed supports, there will be no deflection and no slope. At all pin supports and roller supports, there will be no deflection and no moment. Okay, moving forward, we will use this expression of deflection, which contains 4 unknown constants and 4 integrals of the load function, where we can find deflection expression. We will use this expression in our next numerical problem. Here we have a numerical problem which is concept application number 9.4 from the same textbook. It states that the simply supported prismatic beam AB carries a uniform distributed load W per unit length. Determine the equation of the elastic curve. Equation of the elastic curve, it will be always asked in almost all of these problems in this chapter. Equation of elastic curve is equation of y as a function of x. So we have to determine this expression. We have already derived a general expression here, so we will find this expression. Okay, then determine the maximum deflection of the beam. Maximum deflection is y maximum. Since it is a simply supported beam and the loads are symmetric, so we can say that it will be deflection will be maximum at half of the length when x is equal to L by 2. For all simply supported beams, when loading is symmetric, the maximum deflection will be at half of the length, and if a beam is not simply supported, or if the loading is not symmetric, we have to find a point where y is maximum. It will be maximum where first differential of this function will be 0. Okay. 9.4. A simply supported beam, and A is pinned and B is roller support. It is under a load, uniformly distributed load W. Total length of the beam is L. Okay. We have a fourth order differential equation for distributed loads. It is EI d power 4 y by dx power 4 is equal to minus W. We can integrate this expression. By integrating it once, it becomes EI d cube y by dx cube. This can also be called shear force. Okay, integral of minus W will be minus Wx plus an integration constant C1. Integrating this expression once more, it becomes EI d square y by dx square. This can be called moment, and integration of minus Wx will be minus 1 over 2 Wx square plus integral of C1 will be C1x, plus there will be another constant of integration C2. Let us call this expression number 1. Here are two constants of integration, C1 and C2. We need to further integrate this expression, but before going further, I want to find C1 and C2. It will make our further calculations easier. Since we have two boundary conditions related to moment, at x equal to 0, moment is 0, and at x is equal to length L, moment is 0. So, since both these boundary conditions are related to moment, so I will directly put these boundary conditions in equation number 1, which is related to moment again. Put x equal to 0 and moment equal to 0 in equation 1. We can get C2 equal to 0. Similarly, put x equal to L and moment equal to 0 in equation 1. You can do the calculations part by yourself. I will directly write C1 becomes 1 over 2 WL. Okay, so put back C1 and C2 in equation 1. We get EI d square y by dx square equal to minus 1 over 2 Wx square plus 1 over 2 WLx. Okay, we can integrate this expression again. It becomes EI dy by dx. Dy by dx is theta minus 1 over 6 Wx cube. Since integral of x square is x cube by 3, so it becomes minus 1 over 6 Wx cube. Okay, integral of x is x square by 2, so the next term becomes 1 over 4 WLx square, and here will be a constant of integration, we call it C3. Integrating this expression once more, it will be EIY. Integral of this term will be minus 1 over 24 Wx power 4 plus 1 over 12 WLx cube plus C3x. Here will be another constant of integration, we call it C4. Let me call this expression equation number 2. Here are again two unknown constants, C3 and C4. Let us calculate C3 and C4 using boundary conditions. What are the boundary conditions? At x equal to 0, y is 0. At x is equal to length, y is 0. We have already discussed these boundary conditions for simply supported beams. So by putting x equal to 0, y equal to 0 and x equal to L, y equal to 0 in equation number 2, we can find C3 and C4. Put x equal to 0 and y equal to 0 in equation number 2, we get C4 equal to 0. You can do the calculations part by yourself. Again, put x equal to L and y equal to 0 in equation 2, we get C3 equal to minus 1 over 24 WL cube. You can do the calculation part by yourself. Okay, now we know C3 and C4. We can put back the values of C3 and C4 in equation number 2. So put C3 and C4 in expression 2. We get EIY equal to minus 1 over 24 Wx power 4 plus 1 over 12 WLx cube minus 1 over 24 WL cube x. Rearranging this expression by keeping y on the left side alone and all of the other terms on the right side, we can rewrite this expression as y equal to W divided by 24 EI into minus x power 4 plus 2L x cube minus L cube x. This expression is equation of elastic curve. Let me call it equation number 3. This is equation of elastic curve. It is in the form of y as a function of x. So this is called equation of elastic curve. This was required in the problem statement. The next thing required was, which was asked to determine, was to calculate y maximum. As discussed earlier, since this is a simply supported beam with symmetric loading, so y will be maximum at x equal to L by 2. So we can simply put x equal to L by 2 in equation number 3. Put x equal to L by 2 in equation number 3. We get y maximum. I will write it directly. You can do calculation by yourself. 5 WL power 4 divided by 384 EI. This is the end of the problem. I hope you understand it. I will repeat it once again shortly. We were asked to determine equation of elastic curve and maximum deflection for the simply supported beam under uniformly distributed load. We have started with a fourth order differential equation for load function, which is EI d power 4 y by dx power 4 equal to minus W. Integrating this expression twice, we got expression for moment, this one, which contains two unknowns C1 and C2. C1 and C2 were calculated using boundary conditions related to moment. C2 becomes 0, C1 becomes 1 over 2 WL. Again, By putting C1 and C2 into the above expression, we got this second order differential equation. Integrating this equation twice, we got the expression for slope and deflection. Equation number 2 is for deflection, which contains two unknowns, C3 and C4. The C3 and C4 were calculated using two boundary conditions related to deflection. Putting back C2 and C3 and C4 into equation number 2, we got expression for elastic curve. And by putting x equal to L by 2, since this is a this is a simply supported beam with symmetric loading, so we have y maximum at x equal to L by 2. By putting x equal to L by 2 in equation number 3, we got y maximum. You can do the calculations by yourself. I hope it works. Moving further, our next topic is statically indeterminate beams. Up till now we have solved statically determinate beams. Now we are moving towards solution of statically indeterminate beams. The statically indeterminate beams are those beams which have more number of unknown reaction forces than the number of equilibrium equations we have. For two-dimensional problems, we have maximum 3 equilibrium equations: summation of forces in x, summation of forces in y, and summation of moments equal to 0. But in this beam, we have 3 unknowns at end A and 1 unknown at end B. So total number of unknowns are 4. But total number of equilibrium equations are 3. So we need at least one more equation. For that, we are using this expression of elastic curve, y. But this expression again contains 2 unknowns, C1 and C2. So total number of unknowns have increased from 4 to 6 now. But for this beam, at x equal to 0, we have theta equal to 0 and y equal to 0 because it is a fixed end. At x equal to L, we have y equal to 0. So we have 3 boundary conditions. We can put these 3 boundary conditions into this expression, which contains 2 unknown. But we have 3 equations now, and we already have 3 equations of equilibrium. So totally we have 3 equations of equilibrium and 3 equations from this deflection equation using 3 boundary conditions. We have 6 equations now, and we have 6 unknowns. Which are the 6 unknowns? C1, C2, and this AX, AY, moment, and B. The total 6 unknowns and 6 equations. We can solve this statically indeterminate beam. So let us do a numerical problem on this. Here is a numerical problem, which is a beam fixed at end A and B. We have 3 unknowns at end B and 1 reaction at A, which is unknown. So totally we have 4 unknowns. What we are asked in this problem: for a uniform beam, determine the reaction at A. We have to find here reaction RA. Derive the equation of elastic curve. Equation of elastic curve is y as a function of x, and determine the slope at A. Slope at A is theta A. For this we need expression for theta as well. So we have to start with the differential equation for elastic curve, and then we will integrate it twice using boundary conditions, and we can determine reaction at A. What we have to do is, first we will simply section this beam between A and B. By sectioning this beam between A and B like this, the total length of the section is x. The maximum load was W0. This W0 was for length L. W0 was for length L, but now we have length x. For length x, it will be W0 into x portion of length L. This will be the maximum length at this end. The maximum load at this end. Okay, this is a triangular distribution. So if we want to convert into a concentrated load, it will be area of the triangle 1/2 maximum load W naught x by L into length of the beam, which is x. Okay, simply using statics equation, equilibrium equation, summation of moments at point D equal to 0. So we can find this moment M as this. This moment expression has contains an unknown force Ra which needs to be determined using second order differential equation ei d square y by dx square equal to moment, and putting the moment expression here, we can integrate this expression twice to determine the equation of elastic curve. So by integrating this expression twice to determine the equation of elastic curve, here we have equation of elastic curve which contains two unknowns C1 and C2. These C1 and C2 unknowns can be determined using two boundary conditions, but fortunately we have three known boundary conditions here at fixed end, theta is 0 and y is 0. At roller support, where x is 0, y is 0. So by simply putting x equal to 0 and y equal to 0 in equation number 2, we get C2 equal to 0. Again, putting x equal to 0 and theta equal to 0 in equation number 1, we get this expression. And now by let me call it equation number 3, putting x equal to 0, x is equal to L and y equal to 0 in equation number 2, we get this expression, expression 4. Expression 3 and expression 4 both contain two unknowns Ra and C1. C2 is already known, it is 0. So equation 3 and equation 4, these are two equations containing two unknowns Ra and C1. So simultaneously solving these two equations, we can obtain Ra and C1. Ra was required in the problem statement, so we have calculated Ra. By putting back Ra, C1 and C2 into equations number 1 and equation number 2, we can rewrite the equation number 2 as this: y as a function of x. This is the equation of elastic curve. It was required in the problem statement. Again, we have expression for theta, equation number 1. Putting Ra and C1 into equation number 1, or by differentiating this expression of y, we can get equation of theta. This equation of theta is general expression for slope. At point A, we were asked to determine, in the problem statement, we were asked to determine slope at A, theta A. So at point A, x is 0. Putting x equal to 0 in the expression for theta, we get theta A, which is W naught L cube by 120 EI. I hope you understand this solution. You can do the calculations by yourself, and it was very easy. You can try more problems like this. We will move further to our next topic, which is method of superposition. Superposition is simply addition of multiple quantities. If we have a beam under different types of loads, like this one, this beam is under a uniformly distributed load as well as a concentrated load of 150 kilonewton. So if we are asked to determine deflection at any point, for example at point D, what we have to do is we can split this beam into two beams. Each beam is under a single type of load. This beam is under the concentrated load 150 kilonewton, and the next beam is under a distributed load of 20 kilonewton. The summation of deformations of this loading 1 and loading 2 cases will be equal to the net deformation produced in the given beam. So deformations of beams subjected to combinations of loading may be obtained as the linear combination of the deformations from the individual beams. Okay, these individual beams of case 1 and case 2 similar cases can be found. These are standard. There are some standard expressions for deformation and slope given in the appendix of a textbook, so we can utilize it. This procedure is facilitated by tables of solutions for common types of loading. I will show you in the textbook. This is the textbook for Mechanics of Materials by Beer and Johnston, 7th edition. And if we go to the appendix number D, this appendix shows beams, deflections, and slopes. So we can see it for different types of beam and loading. The first column shows beam and loading. The third column shows maximum deflection. The fourth column shows slope at the end of the beam. The fifth column shows equation of elastic curve. So we can use these this appendix in solving our problems. Okay. Now we will move towards a numerical problem on the method of superposition. Here is a sample problem. Sample problem 9.7 from the textbook. For the beam and loading shown, determine the slope and deflection at point B. Slope means theta at point B and deflection means y at point B. Here's point B. Okay, in order to use method of superposition, we have to split the beam into more than one type of split the loadings into more than one type of loading. For that I will first, before that I want to take you to the table at the end of the book which shows us deflection of beams and slopes. Here we have a cantilever beam under uniformly distributed loads. The beam is totally under uniformly distributed load. The load starts from the fixed end up till the free end. So in order to make our beam similar to this kind of loading, I will add here some load W downward. To balance it out, I will also add some upward load for the same length, W load for half length, L by 2. Okay, we can split this loading into two types of loading, loading 1 and loading 2. Loading 1 is the same beam, cantilever beam, under a uniformly distributed load for length L, downward load. And loading 2 is the same beam under upward uniformly distributed load for length L by 2. We will find at point B y for loading 1 and theta for loading 1. Similarly, for loading 2, you will find y at point B and theta at point B. And then we will add, we will separately find this yb1, yb2, theta b1 and theta b2, and then we will add it like yb1 plus yb2 will be equal to total yb. Similarly, total theta b will be equal to theta b1 plus theta b2. Okay, let us move further to find theta b1, theta b2, yb1 and yb2. Okay, this is our loading 1, which is a beam under uniformly distributed load, downward load W. If we move to the Mechanics of Materials book, here is a uniformly cantilever beam under uniformly distributed load W. If we see in the column number 3, it is maximum deflection. For a cantilever beam, maximum deflection is at free end, this, which is our point B in the given problem. So this configuration is exactly similar to the given configuration where the beam is under load W, the total length of beam is L. So this is our YB1. Similarly, slope at the end, theta at the end. For this beam, there are two ends, end A and end B. End A is fixed, and we know that at fixed end theta is 0. So this slope at the end is theta at end B. So this is our theta B for loading 1. So we can directly use these two values in our numerical problem. Minus WL4 L power 4 divided by 8EI as YB1. Similarly, minus 8L cube divided by 6EI as theta B1. So we can use it directly, theta B1 and YB1, same values from the table. For loading 2, it is a little bit tricky. For loading 2, we have a uniformly distributed load on half of the length only. So I will draw half of the beam here. Portion AC is under a uniformly distributed load W, which is upward in this case, L by 2. This is our point C. This is point A. So first we have to find theta C and YC under loading 2. This is loading 2. So let us go to the table. Here I will delete the previous text. Okay, I will draw a beam here of half length L by 2 and upward loading W. First remember that the given beam, the standard beam, is under downward loading, but in our case loading 2, load is upward, so all the signs will be opposite. Okay, this negative sign will be positive, this negative sign will be positive. Secondly, in the table, length of the beam is L. For our case it is L by 2, so we will simply put L equal to L by 2 in this case, and in this case to find YC. So YC under loading 2 will simply be obtained by putting L equal to L by 2 in this expression. So YC2 becomes W L power 4 divided by 128 EI. Similarly, in this expression, we will put L equal to L by 2. So theta C2 becomes WL cube divided by 48 EI. Just remember, I have used positive sign with both these terms YC2 and theta C2 because our load is upward. These negative signs are for downward load, but in our case load is upward loading number 2. I will use positive sign. So I will put this theta C2, YC2 and theta C2 in our problem here, theta C2 and YC2. Now in the beam, I can see that this is theta C2 and here is, we extend it further from C to B. There is no load between point C and point B. There is zero bending moment between B and C. So the elastic curve will be straight. So theta C2 and theta B2, they are same. Theta C2 and theta B2 are same. Theta C2 has been calculated from the table. We need theta B2, so they both are same. So we can write theta B2 equal to theta C2 as well. Similarly, YB2, how we can find YB2 using trigonometry, using geometry. We can see graphically here, this is under loading 2, y at point B, YB2. It is equal to YC2, this is YC2 plus perpendicular of this triangle. So YC2, this term is YC2 plus this is perpendicular of the triangle. Perpendicular of the triangle can be found as tan theta C2 equal to perpendicular divided by base. Tan theta is almost equal to theta because this is a small angle, is equal to perpendicular divided by base. So this is perpendicular. You can calculate it using trigonometry. Do some calculations by yourself. The sum of these two terms becomes YB2. So now we have calculated YB1, YB2, theta B1 and theta B2. So we can simply add all of them. Theta B1 plus theta B2, the sum is equal to theta B. Similarly, YB1 and YB2, the sum of these two will be YB, total YB. So these sums can be done. You can do the simplification. The total theta B and total YB can be calculated. You can see the solution in your textbook as well. This was what this is what was required in our problem statement to calculate slope and deflection at point B, theta B and YB. What we have done is, actually we have divided the beam given loading into two types of loading, loading 1 and loading 2. For each kind of loading, we calculated theta and y at point B from the table. For loading 1, it was very easy to find it from table 1. For loading 2, we did it for point C, and then we used geometry to first find this YB1, theta B2 and theta C2 equal, and then YB2 from the sum of YC2 and perpendicular of this triangle. Finally, we have added both the thetas and both the y's. Okay. This topic was method of superposition for statically determinate beams. Now we can apply the same method to the statically indeterminate beams. How we can do it? If we have statically indeterminate beam, for example this one, where one end is under, when one end is fixed, which has 3 unknown reaction forces, and the other end is a roller support which has a reaction support RB. So here total of 4 unknown supports are here. What we need to do is first we have to identify a redundant reaction. Redundant reaction is that extra reaction which makes the beam statically indeterminate. For example, in this case, if we remove this redundant reaction, the beam will be like this. So the beam is under a uniformly distributed downward load. In the next stage, we will remove this uniformly distributed load and add redundant reaction to the beam. It will act as a load now. So then these two beams can be superposed onto each other. So the net sum of deformation or net sum of slope of these two cases will be equal to the given deformation or slope of the given load, given beam. So by simplifying it, like method of superposition may be applied to determine the reaction at the support of statically indeterminate beams. Just remember, designate one of the reactions as redundant and eliminate or modify the support. Here we have designated it as redundant reaction, and then we have eliminated it. Then determine the beam deformation without the redundant support. So in this case we may determine the deformation or slope without this redundant reaction. Then in the next stage, treat the redundant reaction as an unknown load, this one, which together with the other loads must produce deformation compatible with the original support. Sum of these two loading, or sum of the deformation under these two loadings must be equal to the total deformation of the original beam. One thing to note here is, at point B there is a reaction, so total deformation is 0, YB is 0. So in loading 1 we can find YB1. Similarly under loading 2 we can find YB2. So YB1 plus YB2 is equal to total YB, which is equal to actually 0. So we can find an unknown from this equation. We can get one equation from here. Other equations are already equations of equilibrium. So we will solve a problem with this method. Here is a numerical problem. Sample problem 9.8 from the textbook. For the uniform beam and loading shown, determine the reaction at each support and slope at end A. Reaction at each support. Here are 3 supports, RA, RB and RC. These 3 are required to be calculated. Slope at A is theta A. Okay, this is a statically indeterminate beam. So we have to apply method of superposition with this beam. Here are 3 reactions at point A, at point B and at point C. Let us consider one of these reactions as a redundant reaction and remove the reaction in first step. So let me consider RB as a redundant reaction, and I am supposing it as an unknown load. First I have removed this redundant reaction in loading 1. So only downward load W is here. In the second stage, I will remove all other loads. In this case it is W load. I have removed load W and applied the unknown redundant reaction RB as load. This is case number 2. Okay. At point B, RB is applied at point B. I will find YB under loading 2 and YB under loading 1. The sum of YB1 plus YB2 must be equal to 0, because at point B there is a reaction, roller support, and at roller support the Y is always 0. So I will find YB1 and YB2 from the table and then put it into this equation, and we can find one unknown from this equation. Okay, let us move. This is our case 1. It is a simply supported beam under uniformly distributed load W. I will go to at point B and we have to find Y. I will go to the table. In here it is a case number 6. It is case number 6, where a simply supported beam is under uniformly distributed load. Column number 3 is maximum deflection column. Here it is. But maximum deflection occurs at the midpoint. In our case, we have to find it at point B. Point B is not at the midpoint. It is at a distance of 2L by 3 from the left end. So what we have to do is, here is another option. the last column. It is equation of elastic curve. Equation of y as a function of x. So in this function, if we put x equal to 2L by 3, we can find deflection at y. Deflection at point B. So here's equation of elastic curve for this beam. If we put x equal to 2L by 3, put x equal to 2L by 3 in this expression, we can find y at point B for our problem. So put x equal to 2L by 3. I will directly show it here. It will be y under yb under load w. They are not calling it loading 1 or loading 2. They are calling it loading w and loading r. So under loading w, yb becomes this much. Okay. Now case 2. Here's case. This was case number 1. This is case number 2. Okay. This is a simply supported beam under a concentrated load. We will go to the table. Here is a case number 5. A simply supported beam under load P. Case 4 is also a simply supported load under load P, but this load is at the midpoint. In case number 5, the load is not at the midpoint. Our case is similar to case number 5, where a simply supported beam is under a concentrated load, but load is not at the midpoint, RB. Okay, RB is at a distance of 2L by 3 from the left end, and remember it is upward. In the table, case number 5 is similar, but the load is downward, so we will just change the signs. Okay, so here is equation of elastic curve. This one we will use when x is equal to a. X equal to a, it means at this point. So here we will put a as, here this is our a, and this is b, this is a, this is b. So we will put a equal to 2L by 3 and b equal to L by 3 in this expression. We can find yb for our problem. So put x equal to 2L by 3 and y equal to L by 3. We will find yb under loading RB. So YBR, we are calling it YBR. The first one was YBW, this is YBR. Okay, we have found y at point B under load W and under load R. The sum of these two must be equal to 0 because point B has a roller support. So there is actually no y at point B, no deflection at point B. So the sum must be equal to 0, putting all the corresponding values of YBW and YBR in this expression. We can simplify it. There is only one unknown, RB. So RB is calculated as this 0.688 WL, and the value is positive, so it is upward. Okay, now we know RB. In this beam, if we know RB, so only two unknowns are left, reaction at A and reaction at C. Now it is statically determinate because this reaction at B is known now. So using equations of statics, we can find RA and RC as well. Both are positive, both are upward. RA becomes 0.271 WL, RC becomes 0.0413 WL. Okay, what else was required? Okay, RA, RB and RC are now calculated. Theta A is required. For this we need an expression for theta so that we can put x equal to 0 for point A and we can find theta A. So again, for this loading and this loading, we will find theta from the table. You can go to the table and find theta, expression of theta. for this case and for this case, we have expressions for theta, slope at end. At which end? At which end? At end A. For this case, it is a uniformly, it is a symmetric load and simply supported beam, so theta will be same at both ends, at end A and at B. For this case, it is different for end A and again something else for end B. So we will take this theta A for concentrated load case and this theta with the negative sign. Why we have chosen the one with the negative sign is because at end A, theta is clockwise. Clockwise theta is negative. So this negative sign is for end A. Theta A for loading W is minus WL cube divided by 24 EI. Here theta A under load R will be this much, where in this case B, what is B? B is, this B is L by 3. Put L by 3, put B equal to L by 3 in this expression and P equal to RB. L is same, E and I are same, so we can calculate theta A as well. So theta A under load W, theta A under load R. Just remember R is upward in our case and it is downward in the given table, so we will change this negative sign to positive. Here it is positive, and then we can calculate theta A under load W, theta A under load R. The sum of these two will be theta A total, which becomes this much, minus 0.00769 WL cube divided by EI. So what we have done is, actually what we did is, we supposed RB as a redundant reaction. We removed it and calculated deflection at point B under load W, and then we applied RB as a load and calculated deflection at B under this load RB. Both the deflections YBW and YBR were added. Their sum must be 0 because at point B there is no deformation. And then we have calculated RB from this expression using statics laws of equilibrium. We have calculated RA and RC as well. Similarly, theta AW and theta AR were calculated from the table, and their sum is equal to theta A total, which is calculated. Let us move to our next topic, which is singularity functions. Singularity functions, this topic was already discussed in chapter number 5 to determine shear force and bending moment in beams. So we will use again the same method. Why do we use singularity function? The singularity functions are used when the bending moment of a beam is represented by more than one functions. For example, if a beam is under more than one kind of loads, so we calculate singularity functions of moment or shear force for each kind of load separately, and then we can add them and we can find a single expression for bending moment of the beam and similarly for shear force. Here are some tables which are given in the textbook. For each kind of load, we have a shear function, singularity function, and a bending moment singularity function. Details of singularity functions have already been discussed in chapter number 5 previously. Similarly, for a uniformly distributed load, for a triangular distribution, for a parabolic distribution, we have different types of shear functions and moment functions. What we need to do is, how can we previously we calculated only shear and moment functions from using these singularity tables. Now how we can calculate slope and deflection from these tables? These tables do not have any function for slope or deflection. They only have shear and bending moment. What we need to do is we will find bending moment function from this table, and then we can integrate the bending moment function twice to calculate shear and to calculate slope and deflection. Okay, how we do it? Here we have a beam. We have to find shear force. We have to find slope and deflection. In this example, this is a simply supported beam under a concentrated load P downward. First we have to find reactions at point A and point B, which are is 3/4P and 1/4P. You can calculate by yourself. Okay, what we need to do is first we have to find singularity expression for moment for this beam. So first load is starting from the left end, our first load is 3/4P. So let us see bending moment function for a concentrated load. It is minus P into x minus a power 1. For this load, our load is upward, so we will use an opposite sign. The load is 3/4P, and our distance from the left end is 0. So A is 0. A is 0 here. So it will be 3/4P to x minus 0 power 1. X minus 0 power 1 is actually x. So we will write it as, with a positive sign, 3/4P into x. For this load, it is a downward load. Our distance from the left end is L/4. So A is L/4 here. It will be minus P x minus L/4 power 1. Minus P x minus L/4 power 1. Okay. Now we will use the famous double derivative expression of moment. D by dx square equal to d square y by dx square equal to moment. We will put the moment expression here. The moment singularity function which has been found from the tables. By integrating this expression twice, we can find slope and deflection. On first integration, it will be EI theta equal to integral of the right side will be the moment function, and integral will be 3/8 px square minus p/2 x minus L/4 power 2 plus a constant of integration. This is first integration, so it is C1. On the next integration, it will be EIY. Integral of the right side will be 1/8 px cube minus 1/6 p into x minus L/4 power 3. Integral of C1 will be C1x, and here will be another constant of integration C2. Again, C1 and C2 are unknown constants, and they can be found using boundary conditions. Similarly, with the method is similar which we have used previously. For each kind of beam, we need at least 2 boundary conditions. For example, in this beam, we have 2 boundary. It is a simply supported beam, so we have 2 boundary conditions at x equal to 0, y 0, and at x equal to L, y 0. Using these 2 boundary conditions, we can find C1 and C2. But remember that anything between these brackets will be equal to 0 if x minus 0 is negative. So we will neglect the whole term if x minus 0 is negative. Okay, let us move to a sample problem on this topic. Sample problem number 9.4. For a prismatic beam and loading shown, determine the equation of elastic curve. Part A is to find y as a function of x. This is equation of elastic curve. Part B is slope at A, theta A. And part C is maximum deflection, which is y maximum. So we need to find these three things. First, to find expression of y, we need expression of moment, so that we can integrate it twice to find y. So we will start with this expression. For this expression we need expression of moment. We will find expression of moment using similar method of superposition. Singularity method, using singularity tables. Okay, before that we need to find reactions at A and B. You can do it by yourself. This is a simply supported beam, so both the reaction at A and reaction at B can be calculated. It is 1 over 2 W naught L. It will also be 1 over 2 W naught L. You can do this by yourself. 1 over 4 W naught L. It is 1 over 4 W naught L. Then if we use singularity tables, here is a triangular load case. The load must be maximum at the right end. This load here is maximum, and it is 0 towards the left side. So in order to make a similar case, we will add some load, triangular load. We have already solved this case in our chapter number 5 for slope and moment only. It will be 2 W naught, because at half of the length it was W naught, so at full length it is a linear slope, so it will be 2 W naught. Here we have to add upward load. It will be 2 W naught here. So a similar case can be obtained. For the downward load, slope is 2 W naught divided by L, and it is an increasing slope, it is a positive slope. For this upward load, it is 2 W naught divided by L by 2, so it becomes 4 W naught divided by L. And since it is a decreasing slope, so it is with negative sign. Okay, using this expression of moment and shear force and load, we can write expressions for distributed load, shear force, and bending moment. You can do it by yourself. We have already done it in chapter number 5 until this point. Just for your understanding, I will just do it for the moment function, how we have done it. Here is a upward load RA equal to 1 over 4 W naught L. So for upward loads, concentrated load, it is downward, we can use opposite sign. It is minus P x minus A power 1. So our case it will be plus 1 over 4 W naught L x minus 0 power 1. So it will be W naught Lx divided by 4. This term is for this load. Okay, then for this increasing slope we have this expression k divided by 6, 2 into 3 is 6, k divided by 6 into x minus a power 3. So it is it is with negative sign, so we will use same thing here with negative sign. K is 2w naught divided by L into x minus 0 power 3. X minus 0 power 3 is x cube. 2w naught by L divided by 6, so it becomes w naught divided by 3L x cube. Okay, for this K2 it is upward load, so we will use the opposite sign, the same function with positive sign, k divided by 6 x minus a power 3. So k is 4w naught divided by L into x minus half of L power 3 divided by 6, so 4w naught divided by 6 becomes 2 by 3w naught divided by L into x minus 1 by 2 L whole power 3. Okay, so this moment function which we have obtained using singularity tables can be put into the double differential function of double differential equation e I d square y by dx square is equal to moment. This moment function is here. By integrating it twice we get c1 and c2. One, this expression is related to y deflection, this expression is related to theta slope. This equation is actually equation of elastic curve if we find c1 and c2. How we can find c1 and c2? At x equal to 0, y is 0. At x equal to length, y is 0. By putting x0 and y0, we get c2 equal to 0 from this expression. Similarly, by putting x equal to L and y equal to 0 again in this expression, we get c1 equal to minus 5 by 192 w naught L cube. By substituting c1 and c2 in these two expressions of theta and y, we can get two expressions for theta and y. This equation of y is a function of x is equation of elastic curve, which was required in our problem part number A. Okay, for part B we have to find slope at A. This is general expression of slope. Just putting x equal to 0 at point A, we can find theta. So put x equal to 0 in this expression, we will find theta A, which is minus 5 w naught L cube divided by 192 EI. Part C was to find the maximum deflection, y maximum. Again, it is a simply supported beam with symmetric loading. So y will be maximum at x equal to L by 2. This is obvious. So simply put x equal to L by 2 in this expression, we can find y maximum, and it will be equal to minus w naught L power 4 divided by 120 EI. So what we have done in this problem, actually, first we extended the triangular load to make it a full triangle similar to the one given in the singularity functions tables. Okay, then we had to add some upward load as well. We have two triangles with different slopes. We wrote moment function for the whole loading, this concentrated load and two triangular loads. This moment function has been inserted into this expression and then integrated twice. We found an expression for theta and y with two unknowns, C1 and C2. These two unknowns have been found using boundary conditions of x equal to 0 and y equal to 0. Also x equal to L and y equal to 0. C1 and C2 are known. They have been substituted into the expressions for theta and y. We have found general expressions for slope and deflection. This expression for deflection is equation of elastic curve. Again, putting x equal to 0, an expression of theta slope, so we have found theta a, and then putting x equal to L by 2 into expression of deflection, we have found y maximum. This was required in our problem statement. Our next topic is moment area theorem. We will study two theorems regarding moment area method. Before this, we have solved and derived expressions for deflection and slope using by sectioning the beams and by integrating the moment functions or by integrating the load functions, and then we have used method of superposition, then singularity methods. Now this is another method, hopefully the last one in this chapter. It is moment area theorems. We previously know that slope is equal to first derivative of deflection, or if we call it d theta by dx, so it will be second derivative of deflection. Second derivative of deflection, d square y by dx square, can also be written as m over ei. Previously we have derived this expression as well. Okay, now we can say that d theta is equal to m over ei into dx, or we can integrate it. Integral of d theta is equal to integral of m over ei into dx, and this integral we can define some limits. For example, if this is a beam and we have different points between A and B, between d theta is change in theta, change in slope. If we want to find change in slope between point C and point D here, so we can set from theta C to theta D. It is valid for any 2 points over the beam. It will be between xc to xd. We can rewrite it as theta D minus theta C, or theta dc is equal to integral of m over ei dx from xc to xd. This is change in slope. Theta d minus theta c, or theta dc, it is change in slope, and this is area under the m over ei curve. Usually we draw moment diagrams. So if we divide moment by ei is a constant number, we can also plot m over ei diagrams like this one. The diagram will be of same shape, just numerical values will change. The numerical values of moment will be divided by ei, and we will get a similar shape of diagram. Okay, under this diagram, area under the curve m over ei is equal to change in slope theta dc. So this area under the m over ei diagram between point D and point C is theta dc, change in slope between C and D, between point C and point D. Here we can see slope of the line at point C and slope of the line at point D. Slope of the line at point C has angle of theta C, and slope of the line at point D is theta D. So this is theta dc. Okay. This is called first moment area theorem. We can define it as theta dc. Here, this is theta dc, this one. Theta dc, a change in slope between 2 points D and C, is area under the M over EI curve, M over EI diagram between points C and D. This is first moment area theorem. Statement of the first moment area theorem. Okay. If we move forward, we can define another moment area theorem here. Okay, for example, here at this diagram, this is the elastic curve diagram, elastic curve of the deformed beam between any 2 points C and D. If we draw a vertical line at C like this one, and we consider any 2 points between C and D, 2 points P and P dash. Let us draw 2 tangents, one at P and the other at P dash. We consider P is at a distance of x1 from point C, and then there is a distance of x dash between P and P dash, which is a negligibly small distance. And these 2 tangents at P and P dash, they intersect the vertical line at C, this line, and these points of intersection are at a distance of dt. Okay, since this dx is a very small number, we consider it almost equal to x1. This distance from C to P dash is also almost equal to x1. So we are considering this as a circular arc dt. We are considering it as x. This angle is d theta and this is dt. So let us apply the equation of circular arcs. We can write it as dt equal to x d theta. Okay, so using this expression dt equal to, sorry, x1, this is this distance is x1, so dt is equal to x1 d theta. D theta from the previous slide, it is equal to m over ei into dx. So we can rewrite it as x1 into m over ei into dx. If we integrate both the sides, integral of dt is equal to integral of x1 m over ei into dx. From xc to xd, we can apply this expression for any 2 points between C and D. So I'm applying it between from point C to point D. This will be TCD. This TCD is a tangential deviation of C with respect to D, of point C with respect to point D. It is equal to this integral, x1 is a distance, remember it, m over ei can be found from the diagram. Okay, if we have m over ei diagram like this one, area under the curve between point C and point D is integral of m over ei dx, then x1 is the distance from point C to the centroid of this area. This is x1. So we can write it as, we can rewrite it like TCD, tangential deviation between point of C with respect to point D. It is area under m over ei diagram between C and D multiplied by x1. x1 is a distance from C. Just remember it. It is distance from the first point C until the centroid of the area between C and D under m over ei diagram. So this is our second moment area theorem. We can define the second moment area theorem like this. The tangential deviation of C with respect to D is equal to the first moment with respect to a vertical axis through C of the area under the m over ei diagram between C and D. This is a vertical axis through C. Okay, and then area under the curve m over ei, and x1 is the distance of the centroid of the area from the vertical axis at point C. Okay, why do we need to find this tangential deviation TCD? What is the physical meaning of TCD, and how can we use this TCD, a tangential deviation of C with respect to D? We can utilize this tangential deviation to calculate deflection of the beams at different points. We will do it in our next slide. We will also use our first moment area theorem. Previously we have discussed it, theta TC and now TCD, both, how we can apply them to the beams. In this slide we can see. Okay, for example, here is a cantilever beam. We always know that in cantilever beam at the fixed point slope is 0. So we know the slope at the fixed point A. If we draw a tangent at A, it will be a horizontal line because it has a slope equal to 0. So we know theta A is 0. Now if we want to find slope at any other point, for example at point D, theta D minus theta A can be written as theta dA. We know that theta A is 0 because it is a cantilever beam and A is fixed point. So theta dA is equal to theta D. So in any cantilever beam, slope at any point can be found by using first moment area theorem. We have to take the fixed point as our reference point because at the fixed point theta is always 0. So we know it's theta. So the difference between between the slope of any point and the fixed point will be angle or slope of the same point, theta d in this case. Okay, so just we have to keep one reference, and that reference should be 0 in this case, theta equal to 0 in this case, which is at the fixed point in cantilever beams. Okay, if we want to find deflection of this point D, we want to find this deflection YD. So again, at the fixed point A, the slope of the line is slope of the tangent is 0, so it will be a horizontal line. So we know that YA is 0. YA is 0. So YD minus YA, because A is our reference now, YA is our reference, it is TDA, tangential deviation of A with D with respect to A, and we know that YA is 0, so tangential deviation of D with respect to A will be actually deflection of point D. So one of the deflection is already known, in this case YA. The other one can be found using second moment area theorem by applying this expression. We can find tangential deviation, slope at any deflection at any point. Okay. Similarly, in simply supported beams, specifically those with symmetric loading, we know that at midpoint we have maximum deflection. Here at point C we have maximum deflection, and at maximum deflection slope of the tangent must be 0. So we know that at point C theta is 0. So by comparing by taking any other point, by taking point C as our reference point, where theta is 0, it is a reference tangent, we can calculate slope of any other point. For example, at point B, theta B will be actually theta BC, because theta BC is theta B minus theta C, and theta C is known, which is 0, because tangent at C is horizontal and the slope of this horizontal tangent is 0. Similarly, we can also find deflection at point C, which will be Y maximum. In this case, it will be tangential deviation between B and C, because at point B, YB is 0. So YC is, at C the line is horizontal, tangent line is horizontal. So we know YB is 0, we can find YC as tangential deviation between B and C, of B with respect to C. Similarly, if we want to find YD here, at any other point D, what it will be, it will be tangential deviation of B with respect to C, TBC, minus tangential deviation of D with respect to C. So it will be TBC minus TDC, because C at point C the reference tangent is horizontal, so we can calculate tangential deviation of any other point with respect to point C. We will do it in one of our numerical problem on the next slide, and you can understand it easily. Before that, since in this method we have to find area under the curve M over EI, so for different types of areas we have expressions. First we need to we want to make areas which are simple, like triangle or rectangle or parabolic area under a parabola or a cubic curve. So here are some standard shapes and their areas. Like for a rectangle, area is given, C is its distance of its centroid point. Here C is from the right end to centroid. Similarly for a triangle, this is area, this is distance of centroid from this vertical surface. Again, for parabolic curve, area under a parabola, here is area, here is its distance from centroid, its distance of centroid from this vertical line. Under a cubic curve, this is area, this is its distance of centroid from the vertical line. Here is any other general curve, this will be n is order of the curve, x to the power n, and this is distance of its centroid from the vertical line. Okay, what we need to do is, sometimes we have, like in this case, we have a very complicated area. It is difficult to find because, like this one, because here are multiple loads. So what we can do is, first we can divide the beam into different simple loads. We can use method of superposition. Like I will do it one here, I will do one of that here. For example, if we have a beam with a distributed load and a concentrated load P and W, we can divide this beam into a distributed load plus a similar beam under a concentrated load, and then we can add, we can draw a moment area, we can draw a moment diagram and M over EI diagram for this beam, and then for this beam separately, and then we can their areas will be simple in the form of triangles or rectangles, and then we can add up those areas. So this method is called bending moment diagram by parts. So we can use this simple method, it will be better. So let us do it. This bending moment diagram constructed from individual loads is called drawn by parts. You can apply this method in numerical problems in the exercise. Here is a problem. This is a simple one. We do not need to do it by parts. This is sample problem 9.11. For the prismatic beam shown, determine the slope and deflection at point E. Slope at point E is theta E. Deflection at point E is YE. We will apply moment area methods, these moment area theorems to calculate slope and deflection at point E. What we have to do in moment area theorems, first we have to draw M over EI diagrams. For that, we first need to find the unknown reaction forces at point B and point D, and then we will draw moment diagrams, and the moment diagram can further be divided upon EI to find M over EI values on the same diagram. So here are reactions at D and B point, which is equal to WA. You can do it by yourself using equations of statics. Then you can draw shear force diagram, which is not required in this problem, but it will be helpful to draw moment diagram. I hope the students can do it. We have already discussed it in chapter number 5. You can go back to your chapter number 5 and revise your knowledge. The same moment diagram can be replotted for M over EI values. Just these values are divided by EI. Rest of the diagram is same. Here in moment diagram, it is WA square over 2. So here it will be WA square over 2 EI. Similarly, all other values will be divided over EI only. Okay. Now, in this diagram, we can see all the areas are either are either rectangles or parabolic curve, area under the parabolic curve. So between, we have to find slope at E. So we have to find we have to calculate all the areas from point E, and in this case, since the beam will deflect like like this beam will deflect like here will be point C, it is a symmetric beam, and tangent to point C will be horizontal line. So C is our reference tangent. Here theta is 0, at point C theta is 0, so we will take it as our reference tangent. We will calculate all areas starting from point C. So the area between point C and point E is divided into two areas. One is area A1, the other is area A2. A1 is simple rectangle, A2 is area under a parabola, because it is a second degree curve. Why it is a second degree curve? Load is constant, so shear force is linear, moment will be second degree. If the moment is second degree, definitely m over EI is also second degree, because EI is constant. Okay, we can find these areas A1 and A2. A1 is rectangle, so it is length into width, L by 2 into WA square divided by 2EI. So WA square divided by 2EI into L by 2. This minus sign shows area is below the horizontal line. Similarly, A2 is parabola, so 1 over 3 into height into base, 1 over 3 height, and base is A. In this case, height is minus WA square divided by 2EI. So we have found these two areas, A1 and A2. Here, here are the calculations. A1 is minus WA square L divided by 4EI. A2 is minus WA cube divided by 6EI. Now we know that theta, first we have to find theta E, slope of point E. Since I have already told here that theta C is 0, this is our reference. So theta E minus theta C will be theta EC. Theta C is 0, so theta EC is equal to theta E, and theta AC will be area under, using first moment area theorem, M over EI diagram between C and E. So between C and E we already have these two areas, A1 and A2. So we will simply add A1 and A2, they are equal to theta E, because theta E is theta EC. So by adding A1 and A2, theta E becomes minus WA square divided by 12EI 3 into 3L plus 2A. If we know the numerical values of W, A and L, similarly E and I, we can find numerical value as well. Now to find, this is slope at E. To find deflection at E, YE, we can see here we know that tangent at point C is a horizontal line. We can find, okay, the deflection is always found from zero deflection. Zero deflection is at point D, because D is at support point. So we will find tangential deviation TEC and tangential deviation TDC, both with point, this tangential deviation of D with respect to C, tangential deviation of E with respect to C. C is our reference tangent. So the difference of these two will be this distance between point D and point E, which is YE. So YE is equal to tangential deviation of E with respect to C minus tangential deviation of D with respect to C. Okay, tangential deviation of D with respect to C, we have to use second moment area theorem. What is second moment area theorem? Let us revise it again. it is area under the m over ei curve between those 2 points, specific points, and then distance of centroid of the area from the first point. In this case, if we have TD, this CD, it is area under the m over ei curve between CD, and x1 is distance from C to the centroid of the area. C is first point. In this case, we have TEC. So TEC is area under the curve between E and C multiplied by distance from first point E to the centroid of the area. So we can see between E and C we have two areas, A1 and A2. Both these areas have their own centroids. So we will multiply those areas with the distance of the centroid from point E. A1 area into its distance from centroid, distance of its centroid from point E. This, it will be A plus L by 4. A plus L by 4. Plus another area. Between C and E we have two areas. A2 is another area. It is A2 into its distance from point E. This distance is a parabolic curve. So from the vertical point it is A by 4 from this point. So from other end it will be 3A by 4. 3A by 4. Okay. This is TEC. Now we have to find TDC. TDC is area under the curve M over EI curve between point D and point C. So between point D and point C we have only a rectangle, area A1 into its centroid from point D, because D is the first point, DC, D is first. So it is L by 4. L by 4. Simply doing some simplification steps, we can calculate YE as this much, minus W A cube divided by 8EI into 2L plus A. If we know the numerical values of L, A, W, E and I, we can also evaluate the numerical values of value of YE. So this is a simple method to calculate deflection and slope using moment area theorem. Slope is calculated using first moment area theorem and deflection is calculated using second moment area theorem. Both the theorems are here. First moment area theorem is change in slope between 2 points is simply area under M or EI diagram. Second moment area theorem is tangential deviation of one point with respect to other, C with respect to D, is area under the M or EI curve between CD into distance of the area centroid from C, this first point, not from the reference point. Okay, so we have applied this theory on these two theorems on our problem, where we had to find theta E and YE. In this problem, C is our reference point because at C slope is 0. So to calculate theta E, we took C as our reference. Theta C was 0, so theta EC is equal to theta E. Theta EC is area under the M over EI curve between point C and point E. Similarly, between point C and E we have area A1 and A2. We have calculated them and added them. To find YE, Y is always deflection of any point from support point. Here support point is point D. So deflection of E with D is YE. So it will be tangential deviation between point E and C minus tangential deviation between point D and C. So this value minus this value, it is equal to YE. TEC is sum of areas under the M over EI diagram between point E and C into their distance from distance of their centroid from point E. So area 1 into its distance of its centroid from point E plus A2 into distance of its centroid from point E minus 40 dc. It is area between point D and point C. It is only one area, A1, into distance of its centroid from point D, because here first point is D. Simply applying simplification steps on this expression, we can calculate YE. After this, I hope you understand it. To understand each and every topic in this chapter, it is not very easy to understand everything from this online lecture. I recommend you to study the book well in depth. The book has a lot of knowledge, and by keeping the textbook in front of you and listening to these lectures and the PowerPoint slides, you can well understand the lecture as well. So after this, there are some numerical problems for exercise which I have chosen. Problem 9.106 recommended for you to solve. Problem 9.9, problem 9.83, problem 9.48, problem 9.104, and some other problems which you also can choose by yourself relevant to these topics. You are recommended to solve these numerical problems using all the methods given and discussed in this lecture. I will upload solution of these problems on my Google site, from where you can download the lectures as well and solution of these problems as well. You can try the problems by yourself, and if you find any difficulty during solving these problems, you can email me at my email address given on the lecture slides and the video description as well. This was our chapter number 9 of the book, which is titled as Deflection of Beams. The chapter ends here. I hope everything is clear to you. You are still recommended to read the textbook while you are listening to these lectures. Try numerical problem. For any discussion or difficulty, you can contact me on my email address. Thank you.